Hello everyone and welcome back to the Analysis 2 course. In the previous video, I introduced the model and presented its objectives, prerequisites, and the main topics that we will study throughout the semester. In this video, we will take you a closer look at the course content. I will guide you through the two main chapters, explain what you are expected to learn, and show how these topics are connected. By the end of this presentation, you will have a clear overview of what awaits you during the semester, so let's get started. The Analysis 2 module is organized into two complementary chapters. The first chapter focuses on ordinary differential equations, where we will learn how to model changing phenomena and solve different types of differential equations using appropriate mathematical methods. The second chapter introduces functions of several variables. Here, we move from one-dimensional calculus to multivariable analysis, studying concepts such as limits, continuity, partial derivatives, and optimization. Although these chapters may appear different, they share a common objectives, helping you understand and analyze mathematical models that arise in science and engineering. So, let's now begin with the first chapter. Our first chapter is dedicated to ordinary differential equations, often called ODEs. Our first objective is to learn how to identify the order and the type of differential equations before choosing an appropriate solution method. Next, we will study several techniques for solving first-order equations, including separable, homogeneous, linear, and Bernoulli equations. We will also learn how to solve second-order and higher-order linear differential equations with constant coefficients. And finally, we will apply these techniques to simplify mathematical models describing real-world phenomena such as population growth and mechanical vibration. These concepts form an essential foundation for many scientific and engineering applications. Before learning how to solve differential equations, let's first understand what they are. Differential equation is an equation that contains an unknown function and its derivatives. It can be written in general form or in a solved form, as shown on the slide. The order of the equation is the highest derivative that appears. Differential equations are widely used to model real problems such as Newton's second law. In this chapter, we will also learn the difference between the general solution and the particular solution obtained by applying an initial conditions. Now, let's move on the different types of differential equation. Now that we know what a differential equation is, the next step is to classify it before solving it. As you can see, the first-order equations can be divided into linear and nonlinear equations. For there, we will study the main types, including separable, homogeneous, Bernoulli, exact equations, and the integration factor methods. During this chapter, you will learn how to recognize each type and choose the correct solving methods. Let's now look more closely at four of the most important methods for solving first-order differential equations. For separable equations, we separate the variables so that each side contains one variable and then integrate both sides. For homogeneous equations, we introduce the substitution u equal y over x prime, which transforms the equation into a simpler form that can be solved by separation of variables. For linear equations, we use an integration factor, allowing us to rewrite the equation in an easily integrable form. Finally, for Bernoulli equations, we perform a suitable change of variables that converts the nonlinear equations into a linear one. Although these methods look different, they all follow the same strategy: recognize the equation, transform it when necessary, and then integrate to obtain the solution. We now move from the first-order equations to second-order linear differential equations with constant coefficients. The key idea is to transform the differential equation into a characteristic equation, which is a quadratic equation involving the variable r. The nature of its roots completely determines the form of the solution. If the discriminant is positive, the equation has two distinct real roots, and the solution is the sum of two exponential functions. Then, if the discriminant is 0, both roots coincide, producing a repeated root and a slightly different solution involving the factor x. Finally, if the discriminant is negative, the roots become complex conjugate, leading to oscillatory solutions expressed with sine or cosine functions. As you can see, a simple algebraic calculation allows us to predict the behavior of the solution. So far, we have studied homogeneous differential equations where the right-hand side is equal to 0. We will now introduce non-homogeneous equations where the general solution is the sum of homogeneous solution YH and a particular solution YP. To find the particular solution, we will study the variation of parameters methods following the main steps shown on this slide. We will also extend these ideas to higher order linear differential equations with constant coefficient. Using the characteristic equation, we will learn how the different types of roots determine the form of general solution. This completes our overview of the main topic in chapter 1. We now begin the second chapter of the course, which focuses on function of several variables. Unlike single variable calculus, where a function depends on one variable, we now study functions that depend on two or more variables. This allows us to model much more complex phenomena encountered in science, engineering, economics, and many other fields. In this chapter, we will develop the mathematical tools needed to analyze these functions, understand their behavior, and solve optimization problems involving several variables. Let's start by introducing the geometric concepts that form the foundation of this chapter. Before studying limits and derivatives of multivariable functions, we first need to define the space in which these functions exist. We begin with the dot product, which measures the relationship between two vectors. From the dot product, we define the Euclidean norm, which represents the length of the vector. Using the norm, we can calculate the distance between 2 points, allowing us to measure how close they are. Finally, we introduce the concept of an open ball and a neighborhood, which generalize the idea of points being close to one another in higher dimensional spaces. These notions provide the mathematical language needed to define limits and continuity in several variables. When studying function of several variables, limit becomes more challenging than one variable calculus. The main reason is that we can approach the same point through infinitely many different paths. For a limit to exist, the function must approach the same value regardless of the path taken. If two different paths produce different values, then the limit does not exist. After understanding limits, we naturally move to the continuity, which ensures that small changes in the input produce small changes in the output. These concepts are fundamental because they form the basic of differentiation and optimization in higher dimensions. The next step is to extend the concept of derivatives of a function of several variables. Instead of differentiation with respect to only one variable, we introduced partial derivatives where one variable changes while the other remains constant. Combining all first-order partial derivatives gives us the gradient vector. The gradient points in the direction of the greatest increases of a function and plays a central role in optimization problems. We also introduced the concept of divergence, an important operator in vector calculus that describes how a vector field behaves around a point. Finally, I want to say that these tools are essential in mathematics, physics, and engineering. The final topic of this course is optimization. Our objective is to determine where a function reaches a maximum, a minimum, or neither. We begin by finding the critical points where all the first-order partial derivatives are equal to 0. Next, we use the Hessian matrix and its determinant to classify these points. Depending on the sign of the determinant and the second derivatives, we can determine whether the point is a local minimum or a local maximum or a saddle point. Finally, we will apply this procedure to practical examples, allowing you to connect theory with the concrete mathematical problems. Optimization is one of the most important applications of multivariable calculus and is widely used in science, engineering, economics, and data analysis. To conclude, this presentation has given you an overview of the Analysis 2 course and its two main chapters, ordinary differential equations and function of several variables. Success in this module depends on regular attendance, active participation, and consistent practice. I encourage you to make full use of the course resources and never hesitate to ask questions whenever you need support. Thank you for your attention. I wish you a successful semester and I look forward to working with you throughout this course.